Hello, you are watching Ako Math channel, and we continue our series of videos called Playing with Spaces. Today's topic is choosing identity elements, and that's about how we choose bases for those logarithms and exponents that we use to define our operations in our ladder of algebras. And I want to show you today as well that we have much more flexibility when we define identity elements. Look at this line on the slide. We can basically put our identity elements arbitrarily on that line. And how to do this will be considered in the second section of today's video. It will be a rigorous mathematical inference of several formulas. I think those formulas will make us much more closer to using algebras, a stack of algebras in practice. And the first part of this video will be more informal. We will go more like a meta level because we need to set the connections between abstract terms of mathematics and some practical observations, some physics, some measurements, so that connection is never like continuous. There is just an analogy that connects them, that match some structures from mathematics to structures that we observe in physics. So that part will be more like a bunch of different analogies and observations that I see similar to mathematics of this ladder of algebras. And you may have some criticisms for this part because it's more like speculative thinking and esoterics at some point. So if you don't like it, just jump to the second part, and I will put both links to the first and second part start in the description to this video. So let's jump to the next slide and start the first section. Okay, I want to start from a line that we used for plus operation. In the middle we had identity element for multiplication, it's 1, and this will be a line of common fractions. We will take this 1 and add it with operation like this or operation like this. And we will get something like 1 over n here, depending on how many 1s we add with this dual addition. And on the right we will have n over 1s again, and this n can grow infinitely. So that's how we basically started this series of videos. So I also want to mention here some dots, but they are like open and side because I want to emphasize that they are not reachable dots. So one dot represents 0, and on this dot represents dual 0, that's infinity. Okay, so for common fractions that we built this way, both 0 and infinity are not reachable, but we can infinitely try to reach them, but we will never reach them. So based on this example, we already can mention several properties of identity elements, like several aspects of identity, and those aspects will allow us to build analogies with some physical observations. So let's talk about first one. So E star is identity element for multiplication operation. So basically we can say that that aspect will be called neutral element. It's a neutral element. Okay, what else we can say about it? So I want to show you that this is actually a quant. So I call it quant because it is a unit of that we use for counting. So for example, object 3, it will consist of ones. So I think that's an aspect that I want to quant unit of count. But counting actually happens with the plus operations, so that's a quant for plus operation. For plus. And let's talk about third property. Let's talk about these empty dots. Those empty dots are boundaries. So they are also identity elements, but for different operation. But they represent boundaries of space of common fractions. Okay? And they are like unreachable bounds or limits. So let me put this property of identity element. Limit or unreachable bound for space in this particular case, for space of common fractions. Okay, so another property that is a little bit harder to explain, but still, let's parse linguistics of identity element term. It's not only element, it's also identity. And what does it mean, identity, here? It's an like representative element. Like, what is your identity? Are you a human? Are you a person? Are you a man? Are you a child? Are you maybe an animal? Or some other, what kind of identity do you have? So in our case, E star represent identity for common fractions. And so I will say that identity element represents some class of objects. It's like canonical element of some set, okay? Class or category or representative. So from these aspects of identity, we can already like set some bridges to physics. For example, speed of light, c. It is not reachable speed for mass, but we can approach it. We can like try hard and get closer to it, but it's not approachable. So in some sense, c is an identity element in sense of free. So we can talk about Planck constants, for example, some like minimal quants that are observable. I don't know, h or something like that. Or atoms, like sizes of atoms, or sizes of, I don't know, molecules. Okay, and we can talk about things like speed of acoustic wave in some media, like speed of propagation of this wave is constant for a media, and it cannot just go higher than that value. We can talk about values like 0 degrees Celsius, where basically the boundary between ice and water or we can talk about value 100 degrees Celsius, like boundary between boiling water and the air. Or let's say we can talk about, how much is that, like 20 micropascal is the minimal pressure that we can hear. Below that pressure our ears do not hear sound. Or we can talk about 20, is that Pascal, 20 Pascal, the max loudness of sound before we have a like pain barrier in our ears. So these are like boundaries of existence for some like some objects. Or we can talk about 20 Hz and 20 kHz, like a range in which we can hear, below we don't hear, and after we don't hear. So these values can be thought of as some identity elements for some specific operations. And let's move on to other analogies. So we have not one axis that I just draw, but we have many, and I want to draw some of them together. So let me draw a line like this. In the middle we will have identity element for plus, which is 0, and here and here we have minus infinity and plus infinity, because these are identity elements for tilde operation, and this is identity element for dual tilde. And we talk about operations like dual tilde here to move upward in this axis, and we talk about standard tilde to move down along this axis. And now let's connect here the next operation in the ladder. So this same point that represent E plus will be a boundary for a next operation, right? So next operation will be E star. This is 1, and it will have dual plus here and plus here, and it will have infinity or dual 0, same as E plus but dual. And again, this axis will have a shared center with the next operation that will be E triangle, moving left with dual multiplication, moving right with multiplication. Again, unreachable boundaries. Here it will be E star dual. It is same as dual 1, and it is same as 2. Let's say if we talk about base 2, it will be 2 to the power infinity. And here on the left the boundary will be like infinite root of 2. So this dot here, and we can move on. So this will be again stacked with another operation that will be corresponding to E square, and so on, so on. So this our ladder of algebras. It looks like this, and it is, we were trying to build a symmetric picture, but this one isn't symmetric because one end is connected to the center of previous line, but another end is just hanging in the air, and I think we'll restore symmetry here later. The reason why we don't have it symmetric here is because the notion of a quant as identity element also has its dual quant. Okay, so we had 0 in infinity and they were present in mathematics. We just showed that this is 0 and dual 0. For quant, mathematics doesn't have dual quant in considerations, but we will restore that symmetry at some point and consider dual quants. And in that case, the free ends of these lines will be also connected to some lines. But now I want to use this picture to talk about this fact. So if we talk about number, let's say 4, sorry, number 4, we can think of it as it is 1 plus 1 plus 1 plus 1, but it is also the same as 2 multiplied by 2. So we have some intersection between operations between these lines. So if I continue this line down here, just saying that actually plus infinity will be here, so this one will be shown as projection of one lines to other lines. So we actually we can project all points of one line to points of other lines. Okay, so this can project here, and this project here, and this project here, and projection can go in any direction, so any line can be projected to any other line. And this is the projection that is reflected here, like same point can be represented in different ways or viewed from perspective of different operations. And in this regard I want to show you something. So let's say here we have some big number. So if you remember, tilde operation is counting zeros, so we can take 0, 0, 0 and do so many of these like zeros, and let's say we got here something like 10 to the power 6. So we have 1 million steps of tildes to reach this point. It is a lot of time to go. But we can reach to this point, as you see with these like arcs. We can reach to this point from a different line, from this line, for example, from this point. So it's the same as we can do a lot of pluses, but we can like 4 pluses, but it's the same as doing just 2 multiplication, 2 by 2. And I want to give an interpretation for this. So you can go this way, this long way, do a million steps, or what you can do, you can change your identity. So basically you drop E plus as your identity and you take a lift. You kind of change your conscious to be another entity. You can go to here, or you can go to here, or you can go to here, and this lift is called exponentiation. So basically from being a cell and requiring 1 million cells, you can just switch your conscious to be a body or a human, and then all those billions of cells will be equivalent just to you, to your identity element. Okay, so if we have all bases like 2, just having 7 layers, moving up 7 times, 1, 2, 3, 4, 5, 6, 7th will be 0. So this number will be already like very big number, much larger than 1 billion. Okay, so basically you can change your identity. That's what I'm saying. You are changing your identity, and immediately you access that scale, that huge scale. And if you that's huge, and you are human and you want a microscope to look at what happens with your cells, you just can do the opposite. You can lift down with log and jump to the micro level. Okay, that's some analogy. And I want to give you another analogy here. So imagine a light beam that propagates through air, and then it reaches some like boundary. Let's say this is a water, and there will be some refraction here, so the angles, these angles will be different. So the beam of light will take the fastest path for it, and due to this desire to take fastest path, it will change the angle, because the speed of light in the air is v1 and in water it's v2, and then v1 divided by v2 will be some sort of the quantity that relates these angles, these two angles. They are different, and we already like connected somehow in our imagination speed of light or speed of wave in one media and other media to identity elements of one media and another media. So basically it kind of can be thought of as, let's say, E triangle divided by E star. And in terms of mathematics, if you have number 9, for example, you probably can reach it the fastest if you take 3 times 2 and then just one step with a plus. So that's an analogy that to reach this point, from this point, you need to choose how many of your path will go in one medium and how large the path in another medium. This is kind of analogy here. You will need to choose which intensity or which operation you want to use and in what amount to reach 9 fastest. Okay, so that's another analogy, and let's move to the next slide. The next slide will be giving another series of analogies, and I want to consider kind of a scale and some levels here. This level will be E triangle. We use it to be equal to 2. Here will be E star, that's 1. Here we will put E plus, which is 0. here we put e tilde, which is in classics minus infinity. And notice minus infinity is not somewhere down below, it's just here on one of the ticks. And below here we'll have E sharp, etc. So for all of these levels, let me draw this picture. So if we start from E triangle, like 2 as an object that we count with, then the operations that we count with will be multiplication and dual multiplication. So I will draw the line, like the arrow here, and we use dual multiplication to move along that arrow. And if we start from 2, the next object after multiplying will be square root of 2. Then we will have cubic root of 2. And then so on and so on. So we will approach 1 infinitely, but we will never approach it because E star for dual multiplication operation is unreachable boundary. So we will kind of approach that one with expressions like this, but it is not reachable boundary. To reach that boundary you need to change identity, so you need to switch from E triangle to E star. Once you switched, you can start from 1. And 1 is a quant, participate in plus operations. So we can say that with dual plus operation we have same story. We can approach 0 infinitely, but we will never approach it. So the numbers here will be 1, 1/2, 1/3, etc. So it's common fractions that we write like this. With 0 same, we will use dual tilde to reach this boundary. Okay, and numbers here will have form like minus n, and so on. From tilde we will go down again. So look at these levels. They are like saturation levels or unreachable boundaries, and I like to think about these levels as about, for example, layers of atmosphere around Earth, or like these boundaries, or it can be like maybe S, P, D, F clouds of electrons in atoms, like energy levels of atoms or things like that. Okay, and those also can be associated with identity elements. Another example that I want to show is, let's say, take axis, and we will talk about frequencies of electromagnetic waves. And if you look at this axis in internet, you will see like all sort of ranges here, starting from 0. There are like radio waves, and then we have something like microwaves, and then we have like what is that? Infrared light, and then visible, and then we ultraviolet, UV, and then we have X-rays, and then we have some gamma rays. So all these limits or like boundaries between these ranges, they can actually represent identity elements for different operations. Okay, that's my understanding how we should map the elements of algebra to reality. And same talk I can do about acoustic waves. Start from 0 Hertz, and then we have 20 Hertz and 20 kilohertz, right? And you know that for our perception, our ear perception, the frequencies transforms to logarithmic scale, and this is what we have for our operations. When we change operation, we use some base, and for hearing, of course, it's logical to have base equal 2, because it will match the practice. So we can easily think that E plus is 0, but then 20 will serve the role of E multiplication, and maybe 20 kilohertz will be E star, and this will be a space of multiplication operation with base 2. As a base for logarithmic and exponentiation. So here I see connection between theory of identity elements and practice. And next section will be about how to ensure that all these values, if you see, I say that E star is 20 and E triangle is 20 kilohertz. When we talk about atmosphere layers, the numbers will be just kind of arbitrary. It will be like 11 kilometers and then 15 kilometers and then 200 kilometers, etc., etc. But in mathematics we have identity elements like you see what they are. 0, 1, 2. So how we connect these completely different ranges? And this is the topic of this next section, okay? So let's see what we can do. So let's start from a case of just two identity elements. It's E0, E plus corresponds to 0, E multiply corresponds to 1. Let's call these values canonical identity elements. Okay, I will refer to them as two canonical. But let's say some space or like that we care about, it actually has two marks, two boundaries that we can measure or observe in practice, and one will be at some measurement of something equal to 10 and another is 100. And we want these actually to make identity elements. This will be identity element for plus, and this has to be identity element for multiplication. But these are not canonical, so I will just like desired. Okay, this circle will be like this. We want to introduce circled plus and circled multiply, so that 10 behaves like 0 and 100 behaves like 1. So what we can see, these are desired identity elements. And the obvious thing is just to take a linear transformation. So we can think of, let's say this is a space F small and this is F capital. So we can transform F capital to F small by some normalization. So let's say we take f, we subtract 10, and we divide by 90. So this L of f will transform 10 to 0, and it will transform 100 to 1. So when we transformed in small f space, we can just use canonical operations of plus and multiply. And after that, we take result and go back. So we can say that if we introduce plus operation, like x plus y, in this form, canonical plus, so we introduce circled plus and circled multiply same way. Multiplied by L of y. So these operations, they will behave for identity elements as we want. 10 will be identity for addition, and 100 will be identity for multiplication. The question is, will distributive law for plus and multiply work? Does distributive law work? So that's the question. And the answer is yes, as soon as we have a linear transformation L, and for plus and multiply we have a distributive law, then this way defined circled plus and circled multiplication will satisfy distributive law. So for two elements we kind of have a solution, but now let's add another element here, which is 2, which is E triangle. And let's say we want 101 to behave like identity element for triangular operation. What we do now? What kind of transformation we use? We can say that, okay, we built a linear transformation for this pair. Same way, because we have isomorphic spaces, we can build linear transformation for this pair. Let's call it, for this one it was L, for this one it will be R, and R will transform 100 to 1, and 101 it will transform to 2. Okay, we can build this, and distributive law will be working for pair like multiply triangle and respectively multiply and triangle. But now we have inconsistency. You see that here multiplication operation defined in terms of R, but here multiplication operation is defined in terms of L. And as soon as we have even more identity elements on our line of identity elements, we will have many of such linear transformations, and whenever we have a formula that involves some numbers and many operations, like let's say we have a formula that will combine like triangle operation and then 2 multiplied by 7, and then we want to use plus operation 15. Let's say they are all circled operation. So this formula involves computations of different operations. So we want to be fair to all of these operations. We cannot prefer one linear transformation over other linear transformations. So what we do here, how can we just solve this problem? And how to do it, we'll see on the next slide. So I want to talk about a linear transformation. So I could write it as it's kx plus d. That's a linear transformation with respect to x. Let me just delete this. But I could also write it as k, some different k already. So x plus d. These are not equal, it's just different form of writing the same linear transformation. And then I just want to write it again in a different form, d plus x. Now you may notice that we can extend this to more operations. So what we have here, correction factor for multiplication operation, k multiply. Then we have correction factor for addition operation. And then we can continue deeper. Correction factor for tilde operation. Okay, and we could go on and go on, but I stop here. And on the other side, again, I can say let's consider correction factor for triangular operation. Okay, and I can say let's take another layer, correction factor for square operation. So this new function here, that's a special form that I introduced. And you can see how you can build this formula, this expression for any number of operations. I will show an example for free operations, but it's easy generalizable. So what I want to show you is how to build it for free operations, and with this formula, let's say k of x equal s triangle k multiply d plus, and we stop our recursion because we don't have correction for e tilde, and then if we don't have correction for e tilde here, then e tilde doesn't change x, we can just use x here. It's like stop of recursion. So what we want from this k of x, we wanted to map our desired identity element for triangle to canonical element for triangle, and same for our other operations. For multiplication, we want to map it to canonical multiplication identity, and want it to map desired plus identity to canonical plus identity. This is 0, this is 1. Let's say we talk about base 2, and then we can set this. And we have a system of equations, and we have s is unknown, k second unknown, and d is third unknown. You can practice a little bit and solve these equations, and I just write out the solution. So the d will be equal to minus e plus. Okay, k will be equal to 1 over e star minus e plus. And s will be equal to 1 over this inversion in a triangular sense. 1 over, and here we have another fraction, but already in multiplication sense. Here is e triangular minus e plus. Here is e multiply minus e plus. So once we got these solutions, so for S, K, and D, you have already you are seeing some similarities here, right? You can basically define this recursively for any number of operations. Once you got S, K, and D, you can now define, so you got this function K. This function K transforms desired E triangle, E multiply, and E plus to canonical 2, 1, and 0. And K minus E inverse, K inverse will transform it back in opposite direction. So we can do the same trick as we did with linear transformation on the previous slide, and we can define a triangular B as K minus first inverse of K, K of A, triangle K of B. This triangle is a canonical triangle. It has identity element equal to. We know how to compute it. So same apply to other, like multiplication operation, multiply K of B, and A plus B is equal common source K of A plus K of B. So these are our operations, and for them you can basically choose any arbitrary values for these elements. Of course, one has to be smaller than the other, so they kind of has to be ordered. I don't know yet if that's requirements or not, or if we can have one larger or smaller than the other one. But for now, let's assume they are ordered from largest to smallest. And for these operations, for these identity elements, we have these operations that will respect these identity elements. Okay. So now the question is, what happens with distributive laws? For these new circled operations that we defined through K and K minus 1, will we get distributive law? And the beauty of this K function is that distributive law will hold. So for each pair of consecutive operations, the distributive law will work, and that is just awesome result, I think. So K of X can be think of as a linear transformation, but it is linear in 3 or more operations. It's, if you draw it on our classical Descartes Cartesian system, it will not be linear. It will be something like this. That will be K of X, and this will be X. But yeah, anyway, it's not linear, but it will preserve distributive law. The final thing that I want to mention is that if you remember, we had a recursive definition for operations. Let's move to the next slide. So for multiplication operation we expressed it, or let's say triangle operation, we expressed it as exp of log of, in terms of multiplication, right, log b. And multiplication, we expressed multiplication in terms of plus, etc. So we had this recursive definition, but now we have what? We have that circular operation is not defined in terms of previous circular operation, but it is defined in terms of just canonical triangle operation. So how we can actually define triangular operation in terms of multiplication operation, which in turn can be defined in terms of plus operation? How can we transit to this nice recursive definition? And it's easy to do, so let's just continue this row. Let's write that it's equal to chi minus first. So now we replace triangular operation with like it is done here, okay? So we get exp, and then we get log k of a, and then we use multiplication now, log k of b. Okay, so now we have here multiplication, and our task is to express multiplication in terms of circular multiplication. For circular multiplication, we have what? Again, just quickly we'll repeat the expression multiplied k of b. We just express this in terms of this, so we reverse this equation. What we'll get? We'll get that sum capital A multiplied by capital B equal k minus 1 capital A circular multiplication k minus first b. Okay, so now we know how to express standard canonical multiplication in terms of circular. And let's now insert it here, okay? So log ka is our capital A, and this is our capital B. It is a bit long expression, but it's worth writing it down. Now k of k minus 1 log k of a, and then we use circular operation k minus first log k of b, and then we close k, we close exponentiation, and k minus first. So there is a long expression, but now we have what we wanted. We wanted to express circular triangle in terms of circular multiplication. Let's simplify this expression. Take a look at this, guys. This one, and this one. What you can see here is that we have this special combination k minus first composition of exponentiation, composition of k, okay, and that function is applied to what? To the same composition but with log. Of a circular multiplication k minus first log k. So you see this like sandwich product, like Verser. I think in geometric algebra it called versors or something like that. So I will denote this expression as x with capital E and this one with log capital L, and this will be log. Okay, so we basically get that A circular B equal x of log of A circular multiply log of B. Same as we had here, almost. So circular multiplication same way can be expressed in terms of circular plus. So now I want to like make a side note. I think it's super important to notice here. Let me just make all this smaller to get some space. So what is important to realize is that you remember how we split identity element, which is 1, on two identity elements, E plus multiplied by E dual plus. That's 0 multiplied by 0, or same way we just introduced fraction this way, 1 over 2 and 2 over 1. So we had this binary split, and now you need to notice that exponent and logarithm that we used, it is also a split but identity mapping, and based on this split gave us multiplication and addition operation at first stage, and then it gave us triangular and multiplication at second stage, etc. So we applied this binary split in our ladder. But the question is, are these the only functions that we can use that split identity mapping and build us this algebra? And as we see here, we made a different split when we used capital X and capital log. We just made another split, but it works exactly the same way. Okay, why this is identity? It's easy to check because like this k will be cancelled with this k, and then this exponent will be cancelled with this log, and this k will be cancelled with this k. So when we compose capital X with capital log, we get identity. Okay, and this is super nice results, I guess. So let's just move on and talk about results. So first we talked about some parallels between abstractions and observations. We talked about what could be those identity elements. Second, we introduced K, a new ladder specific linear transformation that generalize easily to arbitrary number of operations, but I just put it here. K multiply D plus X. We solve it for S, K, and D. I showed in my in my experiments, in my numerical experiments, that distributive law holds. Distributive law holds for operations E star. For these operations have desired identity elements E. Okay. So, and we have we have introduced X as K minus first, X K, similar for log. And we introduce circular operations. Let's say triangle. In terms of capital X log A multiply log B. Same for multiplication operation and plus operation. This is all very easily generalizable to any number of identity elements and operations. We can build ladder based on this K function and this exponent and logarithms. So we have much more flexibility now to build our algebras and use them for practice. Awesome results, I think. Please subscribe, click like, and wait for next videos. Sorry for this long video. Bye bye.